Hello, this is section 1.9 on inverse functions, and we're getting near the end of chapter 1. So the objectives here are to understand the concept of an inverse of a function as a relation. So think back, we talked about relations earlier. We want to use algebra to find the inverses of a function and to determine if the inverse is also a function. We're going to use the horizontal line test on a graph of a function to see if we can tell if that will help us find out whether its inverse is a function, and we want to understand the concept of one-to-one functions. Okay, so inverses. So if f of x equal y, then the inverse of f is written f inverse, and it's a relation that takes y back to x. So it kind of like the inverse, it undoes. So f inverse, it undoes f. If f wraps up a present, f inverse unwraps it. Okay, so here's an example. Let f of x equal x squared. I'm going to give you some examples. F of 3 is 9, so f inverse takes 9 back to 3. So we have that input of the inverse is 9, and then that output of the inverse is 3. Okay. Now let's look at what happens with minus 3. F of minus 3 is 9, so the inverse takes 9 to minus 3. Okay. Now, is the inverse as a relation, is it a function? So think about that, pause, think about it, and hit play again and come to the next, you'll be at the next slide, and that's where I'm headed now. Okay, no, the inverse is not a function. If we want to look back on that slide, the input 9 for the inverse has 2 outputs. That means that's not a function. We saw plenty of examples of that with relations before. A relation is only a function if every input has exactly one output. Okay. Now this is important. Not all inverse relations of a functions are functions. And if a function has 2 x's that go to the same y, then the inverse is not going to be a function. I'm going to take a picture of this. Not take a picture, but show a picture. That's supposed to be y equals x squared. This is minus 3, 9. Yeah, we can do a better job. This is going to be 3, 9. This is the x-axis right here. And notice that if I hit this vertical line, this is y equals 3. There's 2 x's to go with y equals 3. If I go to 2, y equals 2, this is the y-axis, then 2 is going to have 2 x's that go with it. The negative square root of 2 and the positive square root of 2. So the problem here, if we want to reverse things, then we say, well, where does 9 go? It goes to 3 and minus 3. That can't happen in a function. So again, just something to keep in mind. Okay, so we want to look at a different example. F of this should be 2x right here. Because if we plug in 1, we get 6, 2, we get 8. Okay, so this is so here we're restricting the domain just to be the numbers 1, 2, 3, and 4. So we have a shortened version of this function, 2x plus 4. So again, what this means is that f of 1 is 6, f of 2 is 8, and so forth. Okay, now is its inverse relation a function? Pause, think about it. I'll see you at the next slide. Okay, again, this is 2x plus 4. This is how we defined it. And so we want to figure out what its inverse relation is. And remember, the inverse if f of x is equal to y, f inverse of y is equal to x. So that means that here's what f does, here's what f inverse does. So the y of f of x's are the inputs of f inverse. So basically all that means is you switch these around, which I've done here. Now I look, the domain here is going to be 6, 8, this is the domain of the inverse, 10, 12. And notice that no 2 points in domain go to the same place. So each input of f inverse has a unique output. Not like f of x squared. So yes, this is a function. Okay, again, just to summarize, this is f of x equals, I don't know why I left these 2's off, so 2x plus 4. The inverse is here, and the inverse is a function, as we just saw, because no first element of the inverse goes to 2 second elements. They always have unique outputs. And notice that I just want to point something out. This is the domain of f, and that's 1, 2, 3, 4. And here's the range of f. 6, 8, 10, 12. Now the domain of f inverse, 6, just reading it off, 8, 10, and 12. And the range of f inverse is 1, 2, and 3, 4. Now notice that these are the same, and these are the same. So the domain of inverse is the range of function. And that's what this picture is trying to say. F takes x all the way over here. This is 2x plus 4. All the way over here. We don't know what this is yet. Don't want to tell you. And then so the range of f becomes the domain of f inverse. So we take this y value all the way back here to this x. So it undoes it. Okay. So again, I want to define this for all real numbers and would ask, is its inverse a function? Pause, think about it, and see the next slide. So here's the example right here. And what do you come up with? There's lots of ways to answer this, and here's one using the graph. Does it look like there are 2 different inputs for f of x that have the same y? So again, let's compare to what we had before with y equals x squared. If I look at any y value here, let's say y is equal to 3 to 9, notice that y has 2 different x's that come to it, 3 and minus 3. Does anything happen like that over here? And you'll probably figure out, oh, that doubles back. So if I draw any line here and then go down to the x-axis, notice that any y-coordinate just has one x associated with it, unlike over here. Okay, so again, just to summarize, the line is always going up and it never doubles back. Like here, it's going up, but it's going up in 2 directions. Here, there's no doubling. I'm just going to say it never doubles. This doubles here. Since no input has 2 outputs, I think it's a function. Looks to be a function, and the answer is yes. It is a function. Okay, so that's one way to think about it. Look at the graph and see if you can get information. So here's another way. Again, just repeating things here. remember that what the inverse does, F inverse undoes F. So what I'm going to do is I'm going to see what F does, and then I'm going to undo it. So what F does, I'm looking at this, it takes X and doubles it. So in other words, I'm using 5 as an example, it goes to 10. Then it adds 4. And here we get 14. Now we have Y is equal to 14. So I want to recover Y. I want to find out what X is associated with that Y. So I'm just going to do things backwards. I subtract 4 from 14 to get 10. And then I cut that 10 in half to get 5, which is what I started with. So I'm going to try to formalize that. I start with my number, I subtract 4, and then I take half. And I can also, I'm just dividing both parts by 2 to get that. So notice that the inverse, it takes whatever number, so I'm calling X 14, it subtracts 4 to get 10, divides by 2 to get 5. So F inverse of 14 is equal to 14 minus 4 over 10. Yep, 5. Perfect. That's what happens. Okay. So again, and this is a function right here. This is just a line, so it's a function. So that's another way that we saw that this has an inverse that's a function. So the answer here is yes. Let's go to the next one. Okay, so we just found this inverse. Now I'm going to ask a question. What if I take f of x and f of inverse and compose them? In other words, I'm going to plug this into here. What am I going to get? Remember, let's think about this. I would start with 15. F would take it to 5. F inverse would take it back to, F would take 5 to 14. F inverse takes 14 back to 5. So that's what should happen. This is, think about it. It's like going 2 steps forward and 2 back. You're at the same place. So if you apply F and F inverse, assuming it's a function, which it is in this example, you get right back to where you started. 5 went to 14, 14 back to 5. This is like unwrapping a present and wrapping it up again. So again, try this with 2x plus 4 for me. In other words, what I mean by this is try F inverse of f of x. Remember, we talked about composition in the last section. So I want you to tell me what that equals. Here's your formulas. So we're going to go to the next. I want you to do that, think about it, work it out. Meet me at the next slide. Then I'm headed there now. Okay. So again, I want to compose f with f inverse to look at this and see what I get. So look at f of f inverse of x. I hope to get x. Well, whenever I see an x here, I have to plug in this. So I plug in 2x plus 4. So I get 2x plus 4 minus 4, distribute. That's going to be 2x. 2x divided by 2 is x. Yeah. Okay. Good news. Okay. So again, we want to be able to find f inverse when the inverse relation is a function. Okay, so here's our summary. To find the inverse relation, you reverse what f of x does. The inverse relation may or may not be a function. If the inverse relation is a function, then this is going to happen. And also, we didn't do it, but that will happen this too. They undo each other. And we also may be able to find f inverse x by reversing the steps, as we did with this example here again. That should be a 2, and that should be a 2. Okay. So I'm going to use another way to use algebra, and I'm going to go through a procedure, and this will find out what another way to find out the algebra. And we're going to test it out on this thing. So here's the thing. You set y is equal to f of x, you solve for x, and then you switch x and y to set up y is equal to f inverse of x. That's because whenever we deal with a function, we want to always have x as the input. So let's find the inverse relation for this. We set y is equal to f of x, so we get this. Now we're going to solve for x here. So I need to get x alone, so I subtract 4 from both sides. So I get this. Now I'm going to divide by 2, and I get y minus 4 is equal to x. So now what I'm going to do is I'm going to, I get x was equal to that. And then I have f inverse of x is equal to x minus 4, because I want to switch x and y. So this should be, sorry, I did a bad job of that. Here, let me do this part again. I screwed it up. So let's forget this. Okay. So what I did here is this should be x, not y. Because I take y equals minus 4 by 3. I just want to switch x and y. And so over here, this should also be an x. So again, so that's what I get for f inverse. Just to write it clearly, I get x minus 4 over 2. And that's exactly what I got through algebra, is what I got over when I'd kind of reasoned through it before. Okay. So here, I want to find the inverse of f of x equals x squared. We don't know if it's a function or not. Well, actually, we do. We've done this before. But I want you to go through the algebra. Try it, then go to the next slide. And just keep reminding you that you need to take both square roots, unless there's some physical reason not to in an application. But this isn't an application, so that doesn't apply. So I'm going to head to the next slide. See you there. Well, good. I'm going to find the inverse. Now I'm going to go through reason. So to find x squared, we square a number. So to undo it, we take a square root. But since this is not an application, we need to take both the negative and positive square roots. Remember, whenever we solve for a square root, we have to do both square roots. So the inverse relation for this is f inverse equal plus or minus square root of x. And that's not a function since there's 2 square roots. Okay. Now I'm going to find that solution via algebra. So I'm going to set y equal to x. I'm going to solve for x. Then I'm going to switch x and y and set y equals f inverse of x. So I start here, take square roots of each side. X is going to be square root of x squared is x. That's going to be the square root of plus or minus y. And then I'm going to switch x and y. And again, as we saw, that's not a function. For example, if x is equal to 4, y is plus or minus 2. So again, we saw that for a couple of reasons that the inverse of f of x is not a function. Okay, so find the inverse of this. Again, try it, then go to the next slide. Okay, we want to find the inverse here. I'm going to do it both using reason and algebra. So again, I'm thinking 7x minus 16. I want to undo it. This is y. So I've got to undo it. So I subtracted 16, so I'm going to add 16 to y. I multiplied by 7, so I need to divide by 7. So now I need to switch x and y so I can write it as a function. So this is what my f inverse is equal. Now I'm going to do it, I think that's right, but let's see if I get the same answer. So I'm going to use algebra to do it. So the algebra, remember I set y is equal to f of x, so I set y is equal to this. And then I'm going to solve for x. So I'm going to add 16 to each this. Here, I don't need to do this yet. I did this twice. So I'm going to solve for x. So I'm going to add 16 to each side to get rid of that. 16 over here, so y plus 16 is 7x. And then I'm going to divide each side by 7. I do that here. And then so I switch x and y, and so that's my f inverse. I get the same answer. They're equal. So I think I did it right, but there's one more way to check. I'm going to see if I do that, and if I get back x. Remember, the inverse and f undo each other, so if I plug in x, take f, then undo it, I should get back to x. So I want you to do the algebra, and then see me at the next slide. Okay, so I need to check this. Oh, I don't know what happened here. So I look at f inverse of f of x. So here's my f inverse. So I'm going to apply 7x minus 16 here, because that's what that is. These cancel. I get 7x over 7, which is x, which is true. So that looks pretty good. Okay. So we can also, we talked about this a little bit, I hinted at this, and I want to use graphs of a function to see if its inverse relation is a function. And the question is, what does a graph of a function whose inverse is a function look like? We've seen examples. And what does the graph of a function whose inverse is not a function look like? Pause, think about this, and look at the next slide. Okay. So here we go. So here's an example of a function, a graph of a function whose inverse is also a function. And here's a graph of an inverse whose whose inverse is not a function. And remember here the problem is that if I take any output, I'm going to have two x's here. So any y has two x's. Well, any y that's not equal to 0. Okay. And here, if I keep doing that, I have no y has two x's. Okay. So again, I'm hinting at something. Let's see if maybe you'll get it. So think about what I'm hinting at. Is there some kind of test we can do with the graph to see whether or not the function whose graph we're looking at, whether its inverse is a function? Okay. Well, again, if you draw horizontal lines here, what you're going to see is that I'm getting bombed by my kitties. If I draw a horizontal line, I'm going to see that no value of the function of this line has two y. No y has two x's. If I do that over here, I see lots of y's have two x's. This y right here has 2, and so forth. Okay, so we have a test. If a horizontal line hits the graph twice, it means f of x takes two values to the same y. So when you undo f of x to get back x, you get two values of x, not one. So the inverse is not a function. If the horizontal line hits the graph once, as over here, it means that f of x does not take two values to the same y. So when you undo f of x and try to get back x, you only get one value. So the inverse is a function. Okay. So here's one last thing, and this is a technical definition if you see calculus. We'll do one last thing and then summarize. If no horizontal line intersects the graph, then no y value is matched with more than one x value. That's an essential character of what is called one-to-one functions. And a function is one-to-one when each value of the dependent variable corresponds to exactly one value of the independent variable. One-to-one. Each y has one x, each x has one y. So I'm going to say that again. Each x has one y. That has to happen if it's a function. Each y has one x. So that's a one-to-one function. In a function, f has an inverse function if and only if f is one-to-one. So in other words, if f of x is one-to-one, f inverse of x is a function. Oops. It's going to do that right there. Okay. Okay, so to summarize, define the inverse relation, you reverse what f of x does. The inverse relation may or not be a function. If the inverse relation is a function, then we can test our formula by composing the inverse with f. We're always going to get x. We may be able to find f of x by reversing the steps logically or by algebraically solving y equal f of x for x and then finding the formula for that. If a graph of f of x passes the horizontal line test, its inverse is a function. If the graph of a function fails the horizontal line test, its inverse is not a function. If f of x's y values are matched with exactly one y, then its inverse relation is a function, and f of x is set, both f of x and the inverse are said to be one-to-one. Thank you, and please let me know if you have any questions. See you in class.